Just think about how far AI has really come. I mean, not that long ago, we were wowed by chatbots answering, well, pretty simple questions. Now we're seeing systems that can plan complex projects, use all sorts of tools, even collaborate. It's a huge leap, really.
It really is. We're definitely moving beyond AI that just, reacts. These intelligent agents, they have a degree of autonomy, cognitive ability, allows them to actively engage with their environment in ways that are getting, well, quite sophisticated.
Which is exactly what we're getting into today on the deep dive. And we've pulled together some really interesting sources for you. We've got a pretty dense research paper, some articles from Bot Press and IBM, a presentation that breaks down agent structure, and even a study looking at how these advanced agents handle like complex Android environments.
Yeah, and the goal here is really to take all this info, the tech details, the breakthroughs, the hurdles, and just pull out the most important insights for you. Give you a clear picture of where intelligent agents are right now and where things seem to be headed.
Okay, so let's start with the basics then. What exactly is an intelligent agent?
Right. Well, in essence, it's an independent entity. It operates in some kind of environment. It uses sensors to perceive what's going on and actuators to, well, take actions. And these actions are aimed at achieving specific goals. It's this constant loop. Yeah. Perceiving, thinking, acting.
Okay, so like a robot vacuum, sensors see the dirt, the wheels and brush are the actuators, goal is a clean floor.
Exactly like that. And it's not just physical things either. Think about, say, a sophisticated spam filter. It perceives the email content. It acts by moving it to spam, all for the goal of a clean inbox. That fits too. The key is that goal-directed behavior in an environment.
And this idea of a rational agent, that's one that tries to do the best job possible, right? Given what it perceives.
Precisely, yeah. A rational agent aims for optimal performance based on its perception sequence. And there's a useful framework called PEAS. It stands for Performance, Environment, Actuators, Sensors. It really helps you define the main characteristics of any agent you're looking at.
Okay, PEAS. Performance, Environment, Actuators, Sensors. Got it. Now, our sources talk about different types of AI agents. Can you walk us through that from simplest to, well, more advanced?
Sure. You can kind of ladder them up by sophistication. So at the most basic level, you have simple reflex agents. These guys just react directly to whatever they're sensing right now. Think of an automatic door. Senses motion, opens. That's it.
Simple cause and effect. Okay, what's next?
Then you have model-based reflex agents. These actually maintain an internal state or model of the world. So they can make decisions based not just on the immediate input, but also on how they understand the world works and changes.
Ah, so they have a kind of internal map, helps them guess what might happen. So they're not just reacting, they're using this model. That seems key.
That's exactly the key insight. Then, moving up, you get goal-based agents. These act specifically to achieve, defined objectives. They look at their current situation relative to where they want to end up.
Like my GPS planning a route to my destination. It's not just reacting to the car in front, it's aiming for that future state arrival.
Yeah.
That seems significant.
Exactly. And even more advanced are utility-based agents. They don't just have goals. They evaluate different ways to reach those goals based on utility, basically, how desirable an outcome is. They choose the action that maximizes their expected utility.
So back to the GPS. Maybe it considers the fastest route versus the cheapest one with tolls, or maybe the most fuel-efficient one, based on what I prefer.
Precisely. Weighing factors, making a more strategic call. And then the most sophisticated of these sort of traditional types are the learning agents.
Ah, the ones that get better.
Yes, exactly. Learning agents improve their performance over time based on their experiences. They have a learning element that lets them adapt their strategies, become more effective, the ability to evolve to refine their behavior. That's crucial.
Okay, that's a great rundown of the classic categories, but this research paper we looked at, it introduces foundation agents. How are they different? How do they go beyond these?
Right, foundation agents. They represent a more, let's say, complex and integrated view. The key difference, they move beyond those simpler, often fixed perceive-act loops. These agents have evolving goal-oriented cognition. They're constantly adapting their memory, their internal world models, even internal states like emotional responses and reward expectations.
Emotional responses? Wow, okay. That's a significant step up.
It is,
Yeah.
and we'll definitely dig into that a bit more. But yes, the aim is to incorporate more, nuanced aspects of intelligence. Foundation agents can autonomously break down complex goals. They can strategically explore, adjust their behavior through reasoning.
Mm.
And what's really significant is that their internal mental actions planning, strategizing, are seen as just as important as their external physical actions.
So it's not just about reacting smartly anymore. It's about this deeper, continuous thinking, planning, adapting.
Exactly. And the framework they propose is flexible. It can apply to physical robots, software agents, even text-based systems. It's the underlying cognitive architecture that's the defining feature.
Sounds like a lot going on under the hood. What are the key internal parts driving these advanced agents?
The paper breaks it down into several essential components. First, obviously, perception taking in information, turning raw input into observations. Then there's memory storing past experiences, learned knowledge, and they maintain a world model, their internal representation of how the environment works.
Okay, so perception brings in data, memory stores it, and the world model helps make sense of it all.
Precisely. And add to that, these agents can have an emotional state, influencing decisions, they have defined goals they're working towards, and they process reward signals, which helps them learn what actions are good or bad.
Right, so inputs, storage, a mental map, internal states, objectives, feedback. What actually connects that all to deciding what to do?
That's where reasoning comes in. The reasoning function looks at the agent's current internal state, all those things we just mentioned, and figures out the next action. Then there's cognition, which is kind of the umbrella term. It covers both learning and reasoning. It's the whole cycle of updating the internal state based on new perceptions and past actions, and then deciding the next step. And finally, action execution, actually translating that chosen action into something that affects the environment, maybe transforming it first.
It really sounds like they're trying to build something analogous to, well, to the human brain. Is that intentional?
Oh, absolutely. The research paper explicitly points to the human brain as a blueprint, an inspiration for designing these advanced agents. Our brains have specialized yet highly interconnected systems for all these things: perception, memory, reasoning, action. The authors note that many current LLM-based agents kind of stitch these modules together in a more ad hoc way sometimes.
So the brain offers a model for how these different cognitive bits can work together more smoothly, more integrated.
Exactly. The brain manages this seamless coordination. The paper talks about hierarchical and distributed cognition, suggesting AI could benefit from modular architectures with subsystems for logic, emotional appraisal, memory, and so on. And they also stress attention mechanisms, how we prioritize sensory input based on context, goals, emotions. AI agents could use similar learned mechanisms to focus on what's most relevant.
That makes a lot of sense, yeah. So digging into perception then, how are these agents actually seeing or hearing the world? What's new there?
Well, AI perception is moving way beyond just the five senses we think of. We're seeing big strides in audio processing models, like Qwen Audio understanding a huge range of sounds. There's also work on tactile perception, a sense of touch for robots, even exploring things like vestibular sense for balance, proprioception for body awareness. The big thing here is just expanding the sensory toolkit of AI.
That's incredible. Touch, balance, really moving beyond vision and sound.
It is. And unlike us, AI agents aren't limited to immediate senses. They can use something called retrieval augmented perception, or RAGI. Basically, they can pull in vast amounts of external knowledge and merge it with what they're sensing right now. We're also seeing huge progress in image-to-text generation models like BLI, BLAP2, and even text-to-video like Make a Video or Phenaki.
So they can understand images, create videos from text. And what about agents that actually interact physically, embodied intelligence?
Right. That's where vision language action models, VLA models, come in. They take visual and language input and output robotic actions. There's been rapid progress there, moving from older methods to sophisticated transformers that integrate 3D vision and LLMs, things like CLI Port, RT1, Vima. They show increasingly complex manipulation and navigation skills. The critical point is linking language and vision understanding directly to physical action.
Okay, so they're taking in all this data. How do they then make sense of it? Decide what to do. That's the reasoning part, right?
Absolutely. And improving reasoning is a huge focus. High-quality reasoning data is key data that's often carefully checked and verified. What's interesting is that even just fine-tuning large models on this kind of reasoning data can sort of activate or significantly boost their reasoning skills.
Mm.
The insight is that training on the process of reasoning itself is really powerful.
So it's about teaching them how to think logically, not just feeding them facts.
Exactly. For LLM-powered agents, reasoning elevates them from just reactive to proactive. They can process diverse inputs, pull together knowledge, formulate strategies. The environment gives them info for reasoning and also feedback on their reasoning. And people are developing better prompting frameworks, too, to sort of guide the LLMs towards more structured, effective reasoning.
Now, memory is obviously critical for intelligence. How are AI agents handling that? Is it just like a big database?
It's getting much more sophisticated, again, drawing inspiration from human memory. We have sensory memory, short-term or working memory, long-term memory with facts and experiences. The paper mentioned the SPI model of human memory, which highlights different interconnected systems, procedural for skills, perceptual for patterns, semantic for facts, episodic for events, working memory. It's complex. The key idea is this multifaceted, interconnected system.
So the goal is to build something similarly complex and integrated for AI memory.
That seems to be the direction. AI memory involves acquisition, filtering input, then encoding, turning it into a usable format. Multimodal fusion is big here, combining info from different senses, like Jarvis One integrating vision and text.
Okay, so not just storing data points, but combining them meaningfully. What about managing it all? Deciding what to keep, what to forget. Humans forget stuff all the time.
Right, and effective AI memory needs management too. That means forgetting mechanisms, updating information, maybe prioritizing recent or frequently used memories. There are also techniques like expert memory subnetworks being explored to kind of specialize storage and, importantly, reduce hallucinations or inaccuracies when recalling information. The move is towards more dynamic, reliable memory.
Right, because accurate recall is vital. Okay, so beyond memory, agents need some kind of understanding of the world itself, right? This world model.
Exactly. World models are the agent's internal representation of its environment. How it works, what happens if you do X. It lets the agent predict future states. There are different ways to build these. Implicit models kind of encode this understanding within a large neural network. Explicit models, used in things like model-based reinforcement learning, directly learn or model the environment's rules. The crucial bit is that internal representation and prediction capability.
So implicit is more like a learned intuition, while explicit is more like knowing the specific rules.
That's a decent way to put it, yeah. And these world models are fundamental for taking action. They allow for model-based planning, simulating actions and outcomes internally before doing them for real. They also help with exploration, letting agents reason about unseen situations. And this concept helps unify different kinds of data, physical actions, digital clicks, language, because it's all about predicting state changes based on actions.
Building accurate world models sounds like a massive challenge. The paper mentions simulators versus learning from scratch. What's the deal there?
Yeah, simulators provide an external environment, real or virtual, to constantly update the world model. It avoids the difficulty of learning everything just from messy, real-world interactions. But simulators might not perfectly capture reality, and they can be computationally expensive. Learning from scratch is harder, needs tons of data, but potentially leads to more robust understanding of the real world's complexities. It's a trade-off.
Got it. Now, what actually drives these agents? What motivates them to act, to learn? That's the reward system, right?
Yes, exactly. Reward systems are heavily inspired by the brain dopamine, neuropeptides playing roles in motivation and learning. But in AI, reward functions are programmable. We can design them with a lot of flexibility, unlike biological constraints.
So we can basically program what they want.
Pretty much. You have extrinsic rewards tied to specific task goals, but also intrinsic rewards generated internally to encourage exploration and learning, even without an external goal. Think of curiosity-driven reward, rewarding the agent for seeking out new or surprising things. And techniques like RLHF reinforcement, learning from human feedback, use human input to shape what the agent finds rewarding. The key is shaping behavior through these carefully designed signals.
It's fascinating how reward isn't just a score, but it influences attention, how the agent expresses itself, even how it structures memory.
Precisely. As agents get more autonomous, understanding this interplay between reward and other internal parts is going to be vital for building systems that are capable and aligned with what we want them to do.
You mentioned emotional states earlier in the context of foundation agents. How is that actually being incorporated? Are we talking about feeling robots?
Not quite feeling in the human sense, but researchers are drawing on models of human emotion. They're developing LLM agents that can recognize and respond to emotions in more sophisticated ways, like Appraisal-based methods let an LLM evaluate a situation and pick an emotional response that might foster better interaction. The goal isn't genuine AI feelings, but more nuanced, context-aware, and ultimately more effective social behavior.
So the aim is more about understanding and responding appropriately to emotional cues rather than actually feeling.
That's right. The idea is that by understanding and responding appropriately, agents can build better rapport, maybe increase user trust. Frameworks are being explored to align AI behavior with social norms through more human-like interactions. Enabling AI to engage with the emotional dimension of communication is the key development here.
Okay, let's shift to how these agents actually do things. The paper really emphasized tool learning. Why is that so critical?
Tool learning is seen as a really key step towards more general AI. Just like humans use tools to extend our abilities, AI agents can leverage tools, software APIs, databases, search engines, even physical instruments to interact with the world, both digital and physical. The big step is AI using external resources to boost its own capabilities.
So tools let them go beyond just their internal knowledge or built-in skills.
Exactly, and tool systems have evolved, from simple function calls to interacting with graphical interfaces and now even embodied agents controlling hardware. The paper also talks about this interesting idea of action shaping perception, how what an agent does influences what it learns and perceives. It's an active process.
Right, not just passively observing. So what are the main parts of an action system then?
Well, there's the action space, the set of all possible actions the agent can take. Could be discrete, like picking an option, or continuous, like setting a motor speed.
Yeah.
Then action learning, how the agent learns to act effectively, maybe through trial and error or imitation. And tool learning is specifically about discovering, selecting, and using those external tools effectively.
And making sure they use those tools well is crucial, I imagine.
Absolutely. Optimizing tool use means deciding the right tool for the job, getting it quickly, planning sequences of tool use for complex tasks, managing risks, like not letting the AI delete your hard drive.
Yeah, important detail.
Right. And also the mechanisms for learning to use tools better over time. We're seeing this in practice already with AI systems planning and running scientific experiments using lab equipment. The increasing sophistication in how AI uses tools is the key development.
It really feels like AI is starting to automate problem-solving itself by intelligently grabbing the right resources. Now, another really interesting concept, self-evolution. What's that about?
Self-evolution is basically the idea that AI agents could automatically improve their own design, their own capabilities, replacing manual engineering. This could happen online learning and adapting while doing a task or offline, using collected data to refine their overall architecture between tasks. The big shift is towards AI that can autonomously make itself better.
So they're not just learning from experience, but actually tinkering with their own code or structure to improve.
That's the concept, yes. The paper even suggests intelligence gain could be measured by an agent's ability to acquire and use more knowledge, essentially expanding its memory effectively.
This naturally leads to thinking about multiple agents working together, multi-agent systems or MAS. Why is collaboration such a big deal here?
Because many real-world problems are just too complex, too distributed for one agent. Collaboration lets multiple agents pool information, coordinate actions, and achieve more than they could alone. The BotPress article gave the example of traffic management agents for signals, cameras, all working together to optimize flow. The power of coordinated action among many intelligences, that's the key insight.
Like a specialized AI team tackling a common goal.
Exactly. And strategic learning becomes important agents figuring out whether to cooperate or compete, anticipating others' moves. LLMs are even being used to simulate large-scale social dynamics, economics, politics, by having many agents interact.
Wow, that sounds incredibly complex to manage. How do these agents even talk to each other?
Natural language seems to be a dominant way, probably because LLMs are so good at it. Text, maybe voice. It allows for negotiation, discussion. Some systems use more structured information exchange too for efficiency, but language is often central.
And how are these teams, these systems structured? The paper mentioned different setups.
Right, you can have static structures, fixed relationships,
Yeah.
or dynamic ones where agents can join, leave, change roles. Getting dynamic systems fully decentralized, though, that brings challenges with resource sharing, efficient communication, and just scaling up these LLM-based multi-agent systems is tough, distributing the computation, running things concurrently, simulating realistic environments.
And they interact in different ways too, right? Not always just working together on one task.
Correct. Some interactions aim for consensus-reaching agreement. Others focus on collaborative learning, sharing knowledge to improve together. You can also have teaching mentoring setups or purely task-driven coordination, like agents collaborating in Minecraft to build something complex.
So, evaluating these multi-agent systems must be different from testing a single AI. What do you look at?
Yeah, the focus shifts. It's less about just individual task success and more about the interactions, the group dynamics. How well do they collaborate, communicate? For task-solving MAS, there are benchmarks for things like collaborative coding, knowledge sharing, joint problem solving in math, but you also evaluate general abilities, communication quality, resource distribution in collaborative settings, or decision quality and adaptability in competitive ones.
Okay, now with all this power and autonomy growing, safety becomes a huge issue. The paper talks about agent intrinsic safety. What are the main threats there?
They break it down into two main areas: threats related to perception and threats related to action. Perception threats include things like adversarial attacks, someone deliberately crafting input to fool the agent's sensors, or just misperception due to environmental complexity, model limitations, biases, even linguistic ambiguity confusing an LLM agent.
So they could be tricked or just misunderstand the world.
Exactly. Then there are action safety threats, mostly around tool use. Unauthorized actions, maybe an agent gets tricked via prompt injection into doing something harmful. Using the wrong tool, leaking data, needing excessive permissions. Mitigation involves things like running tools in isolated sandboxes, monitoring actions, requiring human confirmation for risky stuff, formal verification methods. The key is managing risks from both bad input and bad output or actions.
And then there's the even bigger picture, alignment, making sure these powerful agents actually pursue goals that align with human values.
That's arguably the central challenge, ensuring that super capable AI systems are beneficial and safe in the long run. Research looks at things like the safety scaling law, how safety relates to capability. It's not always simple. Sometimes more capable models are safer, sometimes less so, depending on the model type and training. The focus is building safety into the core design.
And LLM-based agents have their own specific vulnerabilities.
They do. Misalignment is a big one. The agent's goals drifting from human intent, or its capabilities being misused. Poisoning attacks, where bad data corrupts the model or its knowledge base. Jailbreaking attempts to bypass safety protocols. Privacy threats from agents handling sensitive data. There are defenses being developed for all these differential privacy, federated learning, encryption techniques, system monitoring, adversarial training. But it's an ongoing arms race, really, and they still struggle with complex environments, like that Android study showed, and with certain types of reasoning, like precise math, often needing external tools. Identifying and plugging these holes is constant work.
It's really clear that as agent capabilities shoot up, the focus on safety and alignment has to keep pace, maybe even lead the way.
Absolutely. The progress is stunning agents that perceive, reason, remember, act, collaborate, drawing inspiration from our own brains. It's remarkable. But yeah, the critical challenges remain. Ensuring safety, achieving robust alignment with human values, and making these systems reliable and predictable in the messy real world. That's where a lot of the hardest work lies ahead.
So, thinking about the future, as these agents become more woven into our daily lives, what do you think will be the single most crucial factor for us to trust them, to ensure they actually benefit society? Is it just about raw capability? Or is it more fundamental, something about their safety, their predictability, the control we maintain?
That's the million-dollar question, isn't it? It really forces you to weigh the excitement of capability against the necessity of caution. Maybe the most crucial factor won't be the peak intelligence they reach, but rather how successfully we embed robust safety, ethical considerations, and genuine alignment into their very core right from the start. Not as an afterthought, but as foundational principle.
Definitely food for thought.
Yeah.
And if you listening want to dig deeper into any of this, we really encourage you to check out the sources we mentioned today. Continue your own deep dive into this incredibly fast-moving field.